Hi, and welcome back. In the other parts of this trick, we talked about factorials, combinations, and how you can find them in the Pascal Triangle. In this part, we're going to be talking about two theorems that come up pretty often and can help you cut down the amount of time you use to solve these types of problems. The first one is already written on the screen, and it's Pascal's identity, which is saying that n choose r plus n choose r plus 1 is equal to n plus 1 choose r plus 1. If this is a little confusing, we can do an example. For example, 5 choose 2 plus 5 choose 3 is equal to 6 choose 3. And you might question whether this is true or not, but let's see. 5 times 4 over 2, that's equal to 10. 5 times 4 times 3 over 3 times 2 times 1 is again 10, equal to 6 times 5 times 4 over 3 times 2 times 1, which is equal to 20. And indeed, 20 is equal to 20. But what if it only works for these three combinations? Or maybe it only works for the first couple of rows. I don't want to continuously test it for all the combinations. Like, there's infinite. So let's try a more algebraic approach. Let's use these variables to prove Pascal's identity. Basically, n choose r plus n r plus 1 is equal to n plus 1 r plus 1. And as a reminder, n choose r is just equal to n factorial over n minus r factorial times r factorial. So let's write each of these terms in terms of factorial. So that's the first one, as we just saw. Second one's going to be not n factorial at the top, times r plus 1 factorial times n minus r minus 1 factorial. And that's just equal to n plus 1 factorial over r plus 1 factorial times n minus r factorial. Okay, so what can we do with this? Maybe we can try some cancellation, but what is there to cancel? Maybe we combine all the terms, but then that gets really, really complicated. Ooh, maybe what we can do is convert this r factorial into the r plus 1 and the n minus r, or the n minus r minus 1 into the n minus r. So let's multiply, and if we want r plus 1 factorial and we have r factorial, then we just multiply r plus 1. So let's do n factorial times r plus factorial over r, not the factorial, plus r plus 1 factorial times n minus r factorial plus the n factorial over the r plus 1 factorial times, you'd have to convert this into n minus r by multiplying n minus r to both the numerator and the denominator. And then we're just going to get the same purple thing. I'm just going to do a small purple squiggly. Then we can combine these two to get n factorial times r plus 1 plus n minus r factorial over n minus r factorial times r plus 1 factorial. And as we see, this is equal to n factorial times n plus 1 over n minus r factorial times r plus 1 factorial. And this right here is equal to this, because if we multiply these two together, you do get n plus 1 factorial. So now that we've proved the Pascal's identity, let me just erase all the ink. How is that going to help with this problem that I've selected at the top? Well, we know that 4 choose 2 plus 4 choose 3 is equal to 5 choose 3. But there isn't anything else we can do after that, is there? This is where I will introduce the second trick, which is n choose r is equal to n over n choose r. And for example, in the Pascal triangle, that's like saying that this term is equal to this term. And we can first prove this by just saying that there's symmetry, and then this term is equal to that term, but that isn't a really concrete proof. So we'll do what we did with the Pascal identity and expand this, saying that n factorial over n minus r factorial times r factorial is this first term, and that's also the second term. So they are equal. Another way of saying it, which is how I've been saying it the past couple of times, is saying that picking r objects in is equal to picking n minus r objects out. So how is this helpful? We can say that here we can say that 4 choose 3 is equal to 4 choose 1. So a new equation we have is 4 choose 1 plus 4 choose 2 is equal to 5 choose 2. And now we have what we want in the problem. So we can just substitute the values and get 5 choose 2 equals 10. And I know that you could have just done 5 times 4 over 2, but if on a test you have more complicated or higher numbers instead of 4 and 5, then you can use a similar process instead of actually having to calculate it. So I hope these two theorems help you in the future, and I hope you enjoyed. See you soon.